Okay, this is typically used to represent, we need a representation. We're looking at some details also because this is the gold standard for measurement. Stick diagrams are used. Stick diagrams are simpler, allow easier scale up to represent splits when multiple nuclei are considered. The stick diagram for split in energy levels with one nucleus is as follows. You have one energy level represented by the stick, and when you bring in one proton or one, let's say one nucleus, proton, good enough, this energy level splits into these two. And the energy spectrum, the final energy spectrum is something like this. The derivative dE dH is like this. These are typically used to represent the various simple interactions. So now you know why EPR can be very complex. The principles, all the principles that go towards generation of the spectrum are all very fundamental, fine. But you have a complex set of interactions in any system, and therefore, as long as you have simple enough and only that species present, the interpretation is very straightforward. Otherwise, deconvolution is quite a pain. In fact, this happens to be the hydroxyl radical spectrum when only that is present. Okay, so it has two splits. We typically represent these as splits, so it has two splits. And all EPR spectrometers are directly programmed to give you the DE/DH spectrum, because that happens to be more useful for interpretation, especially for recognizing the radicals. The derivative spectrum is directly used. So if you need the energy spectrum, you need to go and integrate this once. If you need the area under the energy spectrum, which is proportional to the concentration, you need to double integrate this. That's what we typically do. If the interaction of two equivalent protons are considered, again, two equivalent protons, the split in energy levels is something like this. The one gets split into two, and then each one of this, due to its interaction with the other proton, gets split into this. And typically you have three levels, four, but two overlapping levels. So three levels with 1:2:1 ratio. So the energy spectrum would look something like this, and the derivative spectrum would look something like that. If this can be extended, okay, it can be interaction with many protons. So this is with four protons. So if it is, we have already seen, if it is with one, it is 1:1. If it is with two, 1:2:1. If it is with three, it happens to be 1:3:3:1. Okay, equivalent protons. Four, it happens to be 1:4:6:4:1, and so on and so forth. The 1:3:3:1 happens to be like this, which and this 1:4:6:4:1 happens to be something like this. Okay, take a break and do some attendance. So does all your workflow issues are all settled right now? You don't get any more notes from the people. Anybody having any issues with workflow or any of those formality issues? This thing is fine. Digi is fine. What I did was waited for a bit, and then I wrote to that person with a list. They're trying to match the list that is available is always a challenge for them. Takes a long time. Never happens actually. And not just that, some have not um, uh, dropped the courses yet. People who have dropped it, I think one still. I told that person, he said that he has a problem with his workflow. So whenever that happens, time is there, but dropping time is there. but it will show up, and if it shows up here, it will show up on the attendance sheet. So every time I'll have to mark absent. Then if that remains, unless I give a W to that person, the other grades will not get accepted at the time of giving grades. And if I do that, the other person has to run around, a lot of running around. It is not very easy to tell the person sitting there that I didn't attend the course. I'll give all the letters, but it's a big pain. So I told the person, but let me check academic, right? Ah, so this is even the academic site gives the correct list. But what I did was I sent the list of names to that person and update the list with this. The person updated it probably 2-3 weeks ago, so it was fine. Soon after the ad drop period, I sent the list. So that way it was okay. I've been at peace for the past few weeks. And just log out. Okay, people, it's time that you start looking at your leverage RS exercise. Start thinking about it at least. And of course, the critical review is quite straightforward in terms of compared to the leverage RS. It's not as creative as the leverage RS, but that also will need quite a bit of time. So please start thinking about those. Those would contribute significantly towards your grade, apart from um, your incentive quizzes. That's mostly for making sure that you've picked up some marks for that and so on. Okay, so that's 10%. I think the remaining is these two exercises. So please make sure that you do a good job. And for the uh, for the incentive quizzes, I'll give you some papers to read for sure. In addition, there will be some papers that you can read. There are also papers in the same sub area of our work, but I cannot give you 10 papers to read for just one area for a class. So I've selected about 3 or 4 to read. I'll give you time. We'll typically not meet the class after which I assign those papers, so that you'll have one class time to read at least. And then the next class, as soon as you come in, there will be some 10 minutes of open notes, open quiz, open notes, open book, open everything quiz, and then we'll get on with our discussion of that material. Okay, so that way you'd be prepared, and then your thinking would be at a different level in that particular small area, and that discussion would be at a different level. I'll have a set of slides to present anyway, but it'll be mostly on a discussion mode. That's the whole idea here. So good, please start doing. In general, n equivalent protons give a spectrum of n plus 1 hyperfine splits. If Im represents the energy absorbed by the mth line, their intensities are given by this combinatorial formula, n factorial by n by 2 plus m factorial times n by 2 minus m factorial. That's the intensity of the mth line. Okay, so we had 1 is to 4 is to 6 is to 4 is to 1 and so on and so forth, right? So that in the earlier case, all that will come out of this formula. And of course, the values that m can take are quantized. So this is some place where we kind of represent the quantized aspects in a classical view. A classical view is just limited to looking at the electron going around and so on and so forth in this case. Okay. And useful characteristics of the EPR spectrum are as follows. I'm not going to get into these, I'm just going to mention these. The value of the applied factor, applied magnetic field H at which the resonance occurs, which is determined by the G factor, right? So that is one important aspect. area under the absorption curve that indicates the concentration of the reactive species. That's another important calculation that we make. The number of spectral lines, the separation of lines, the width and shape of individual lines also give useful information. And of course, we have not looked at the detail. Only if you get into that area is it even relevant to look at the detail. So, you could do as needed in the future for this. That is a typical EPR spectrometer. That is how it looks. It is very similar to the one that we have in our SAFE, which is right across here. So, this is the magnet. And you see these huge things. These are huge electromagnets. 15,000 Gauss is very simple. I think this is much higher. I think this is our machine. Have I given you any reference? No. Most likely our machine or something very close to our machine. From that brochure I might have taken this. And our setup is very similar to this. If you look at, go and look at it. I think so. It's been many years since I looked at it, but and that is the magnet. Okay, you have large electromagnets here. This is the EPR tube, a special quartz tube, in which the sample sits, and it sits in between these two magnets. That's the way the measurements are made. So, let us stop. We have probably 9:43, so 7 minutes left. Please watch this video and then we will stop there for this class. Do we have anything more? Yeah, probably I can. Okay, before you start this video, you can probably watch it at the very end. The earlier 1:2:1 spectrum, I said it's for hydroxyl. Okay, that's for native hydroxyl. It was quite easy to see interaction between a proton and an electron. Okay, many a time we use something called spin trap to capture the reactive species and measure it after some time. Okay, it's essentially like freezing the reaction at that point in time and then measuring it later, because these things change fast, right? So, you want to measure at a particular point, you capture it at that particular point into a stable radical and then measure the stable radical later. Those stable radicals are called, relatively stable radicals are called spin traps. The spin traps interact with the radicals and form reasonably stable free radicals. The stability can last for a few hours and the measurement becomes easier with their use. And this is some example. DMPO is something that we have used heavily for capturing hydroxyl radicals. The DMPO OH is this molecule, hydroxyl radicals, and the spectrum will be something like this. Okay, no longer 1:2:1. You have a spectrum which represents this molecule, okay, or this free radical environment in this molecule, which will be something like this. Okay, so essentially you spin trap and then say the spin trap is going to give you this, and therefore this is the amount of hydroxyl radicals that are present if only the hydroxyl radicals are present. If something else is there and you use some other spin trap or some other radical and so on and so forth, what you get will be a composite spectrum. Okay, there is no way to split the various composition contributions at that point in time. You can do a deconvolution, that is a more involved process. So, DMPO is one common thing. There are many common things. I think there is yeah, this table might be there in your I am not sure, very sure whether I uploaded this, but this gives you some list of spin traps, and these are available in your textbook. Tert nitrosobutane. I will just read out these. PBN, I am more familiar with these. PBN, DMPO, DMPO heavily, we have heavily used, BNB, and so on and so forth for various radicals. They are specific for various radicals. Okay. Fine. This biomarkers will take up tomorrow, Monday. Please watch this video. This is the last video in that file, I think. I mean, rather in that chapter, or probably in the file. Is there any other video? Yeah, there could be some other videos too. So, in the chapter at least, please watch this and then we will close for today. Okay. So, see you on Monday at 12.